video problem number 96, electrical energy from oxidation reduction reactions. So we're going to take a look at the reaction that we balanced in 94B, and what I have here is an abbreviated table of reduction potentials. So in other words, for this reaction, which is a reduction reaction, we can tell that it's a reduction reaction because we are gaining electrons. For this reaction, it gives off 1.33 volts. Alright? This reaction gives off 0.835 volts. So what we need to be able to do is figure out what's the total voltage that's given off. Now, for any voltaic cell, it is a spontaneous reaction, which means we have to have a positive voltage. So again, it's spontaneous, which means positive voltage. Okay? Now these are both reduction reactions. We can't have two reduction reactions, which means we have to flip one of these two reactions. So which one do we flip? Well, we flip the one that's going to give us an overall positive voltage. Right? So let's look at our two options. Here's reaction A, here's reaction B. Let's say I flip reaction A. Right? So let's say I flip this one, I reverse this one, so I end up with 2 chromium 3 plus 7 waters yields Cr2O7 2 minus plus 14 protons plus 6 electrons. That means my voltage, since I flipped the reaction, my voltage is now negative 1.33 volts. And then if I keep the other reaction of 0.835 volts, notice when I add those two up, I get a negative voltage. And you can't do that. So obviously we're not flipping reaction A. So I'm going to flip reaction B. Okay? So I'm going to go ahead and write reaction A. Now notice reaction A is completely balanced. So that's a balanced reduction reaction. I've got the same atoms and the same charge on both sides. It's a balanced reaction. So that's, let's see, let's go ahead and write it down. Cr2O7 2 minus plus 14 protons plus 6 electrons yields 2 Cr3 plus 7 waters. Now if you look at a table of reduction potentials, you'll see something like this. Okay. Now unfortunately you're not always given a table of reduction potential. Sometimes you're just given voltages, but somehow you have to figure out what the voltage is. Okay, so I'm going to flip this second reaction. I'm going to flip reaction B. So that means I got NO2 minus plus water as reactants. So as products, I've got NO3 minus plus my 2 protons plus my 2 electrons. So now my voltage is negative 0.835. Okay, but notice that my electrons don't cancel out. That means I need to multiply the bottom reaction times 3, right? Because I got 6 electrons here, 2 electrons here, electrons have to cancel out. But just because you multiplied the bottom reaction, you do not multiply the voltage. So the voltage stays as it is. So let's put 3, 3, 3, 6, and 6, right? So now let's add this up. My electrons cancel out, they always have to. My 3 waters cancel out. I get 7 waters up here, so it gives me 4 waters as a product. I've got 6 protons, 14 protons, so it gives me 8 protons right here. Right. I've got my 3 nitrites, and I've got my dichromate. Alright, that looks good. I've got my 3 nitrates, and I've got my 2 chromiums. So that should be mass and charge balance. Go ahead and check it. Then for the voltage, I just add them up. So 1.33 minus 0.835. And I get a voltage of 0.495. So with all of these redox reactions, there is only one way where the voltage can be positive. Okay? So you're gonna flip one of the reduction reactions. You're going to flip the one so that the overall voltage is positive. So that's how you know which one to flip. And know that the opposite reaction, so we flipped B, the opposite reaction of this is non-spontaneous, so it wouldn't work. Okay?